Hi, so let's continue with the separation, right? We were looking at separations. So now, again, this we started off with this case, right? So what we're essentially looking at, what we're essentially looking at is the del 2 del y, this value. So the del 2 del y, del 2u del y2, at the wall, right, and the boundary at the edge of the boundary layer, right, and that's how we're kind of defining that how the shape of the velocity profile of should look like, which is the profile of u, right, how the u should look like. So essentially, right, so we are kind of looking at the value of del 2u del y2, right, which depends on the, as you can see, the pressure gradient as well as the free stream velocity gradient. And what we are basically saying is that between the edge of the boundary layer, right, this is the edge of the boundary layer, this one is the edge of the boundary layer, and this one is the wall, how these slopes should look like, so that we can comment on the shape of the boundary layer. And from here we are going to sort of talk about how separation occurs. Now the first case that we said is that both of these, the del 2u del y2 is negative both at the wall as well as at the edge of the boundary layer. Now it's going to be negative always at the edge of the boundary layer, to merge into the free stream smoothly. So I think you can figure that out yourself, but I can come back and sort of, if I have time, I will give you little hints about how to do that. Except basically when you say del 2u del y2, this is nothing but slope of a slope, del y of del u del y, right? And so if you were to look at this, right, so use this understanding, and at the edge of the boundary layer where this u is very close to the free stream, right, and then this should give you an idea that why I'm saying that del 2u del y2 near the boundary layer is actually negative. It's always negative. Okay, all right. So now going to the next one. Okay, so going to the next one. Okay, so we started with dp dx being negative, right? Now we're saying dp dx is equal to 0. And what we have seen in the previous module, that the dp dx, being negative or positive is basically affected by the shape of your body, right? So dp dx is 0, right? Because if the flow is accelerating, you have dp dx is negative, right? And vice versa. So if there is constant flow or non-uniform and uniform flow or stagnant, then dp dx is 0, which happens for the case of a flow or a flat plate. So this is nothing but flow over a flat plate, right? Now, so in this particular case then, okay, if dp dx is 0, then del 2u del y2, right, at the wall is 0, right, which means if I integrate this, that del 2u del y, right, at the wall is a constant, right. So which means that del 2u del y is a constant, which means there is, so in this particular case, which means that there is a linear growth. There is a linear growth. So what I mean by that is that if I had to sort of, again, draw this, okay, so this is my wall somewhere, okay. Okay. So before I do that, let me draw this and say this is a linear growth, something like that. Okay. So your slope is something like that, which means that this way. Okay, it's linear in this region. That's what it means. And of course, here it is u infinity and so on and so forth. Okay, so this is linear growth. Okay, that is u infinity. This is u y. Okay, and this is of course delta. Okay, and again, of course, we have tau wall, right? So tau wall is always going to act. This is tau wall, right? So what we're basically saying in this particular case, again, right? So this is 0. Del 2u del y2 is now 0. So in a sense, now del 2u del y2 is now 0 at the wall. Okay, and this is negative, of course, at the edge of the boundary layer. What we had earlier is that this is kind of negative at the wall. Okay, negative at the wall. So you can think of the thing that, you know, del 2u del y2 is basically telling you that it gives you, it's like I said, it's del del y of del u del y. So it's the change in slope that you're looking at. So the change in slope, so what you can see here is that between the wall, the first case, between the wall and the edge of the boundary layer, both there is no change, both are negative. So that means there is no change in slope as such here. So, but then this is negative here, so there should be an inflection point which should be somewhere inside, you know, which is inside this wall somewhere. Okay. Now, in this case, however, you have a positive, it is 0, right? Del 2u del y2 is 0 here and negative here. All right. So in this case, the point of inflection is actually at the wall, because then beyond 0 it will become negative, right? This part is so the inflection point is therefore here, right? So here it becomes linear, and then at the edge of the boundary layer it is negative. Okay. So this is the second point here. Okay, so again, there is no separation here. Okay, there is no separation here. And now the interesting thing is that we are going to look at this, right? So now the next thing is we'll look at basically the adverse pressure gradient. So in this case, okay, we're looking at adverse pressure gradient where dp dx, okay, is this, and d infinity, right? So it is basically a retarded, you know, flow, okay, retarding flow, okay. So now in this case, therefore, you know, as you can see, that del 2u del y2 at the wall, right, at the wall is actually positive, right, is actually positive, which is positive, right, and we know that del 2u and del y2 at the edge of the boundary layer, right, is negative, right, is negative. So therefore, there is a change in slope within the wall and the edge of the boundary layer, right, somewhere in between where, so it goes from negative, right, at the wall, so sorry, it goes from positive at the wall to negative at the wall. So there has to be an inflection point somewhere, okay. So let me see if I can sort of, you know, draw that picture right. So what I mean is, so this is the wall, okay, and okay, so now you have a positive, okay, you have a positive, something like that, okay, or maybe I make it a little more sort of steep, say something like that, okay, and in that case, if I were to draw something like this, okay, if I were to draw something like this, right? If I were to draw something like that, so you can see that there is a certain change in slope around this point, right? Around this point. So this is the slope here, right? So let me erase that bit. You can sort of imagine that. So what you can see is around this point, there is a change in the slope, as you can see, right? So because throughout this point, it will be along this orange line that you see, but after this here, the slope changes, right? So let me sort of elaborate on that a little bit. So till it reaches before this, from the way I've drawn the curve, what I see is the slope is somewhere like this, right? But after that, okay, so this is positive, it is kind of positive, and after that, so around this, right, moment it crosses that, so somewhere like that, the slope is this, right? So you can see that the slope basically is now decreasing, right? It's positive, and then so now it decreases and it becomes 0 around this point, and then it will actually it will become negative as we go to the edge of the boundary layer. So that's what this essentially means. So you have your velocity profile like this. So this is the inflection point. Okay, this is the inflection point, which we shall write here. Inflection point, right? Of course, you have tau wall. Okay, and this is again delta. Okay, and this here is u infinity. This here is u infinity. So therefore, in this particular case, okay, now point of inflection is again within the flow, right? The point of inflection is basically in the flow, okay. No separation. Is that right? Okay, so in this here, okay, now okay, so now the point is that where do you think this, now the question is, where do you think the position of the inflection point should lie? Well, clearly it depends on how much positive or how much negative, as you can see here, right? How much positive is it, and it is how much positive depends on the pressure gradient. So therefore, the position of this point basically depends on the strength of the pressure gradient, right? So position, okay, IF is basically inflection point. Okay, I don't think I wrote that anywhere. IF is basically inflection point. Well, this is basically the point where a curve changes slope. Okay, there is a change in slope which is happening at the inflection point. Okay, so the position of the inflection point depends on the strength of the pressure gradient. Right? Okay. Now, for weak gradient, flow does not separate, but is close to transition to turbulence. Okay. Yeah, so well, for a weak pressure gradient, this will not separate if you have a weak pressure gradient, but it is actually close to it. So if for transition to turbulence at, for example, REX around 0.1 million, okay, you will see a velocity profile similar to this, and it is close to transition to turbulence. Okay, so basically the flow will transition to turbulence before it separates. Okay, so here around at around 0.1 million, so that will happen at 0.1 million. Okay, now the next thing is if I come here, so now moderate gradient, right? So a critical condition is reached, right? So a critical condition is reached where, okay, so dy del y del u by del y is equal to 0. Okay, what does that what does that imply? Okay, so at a critical, let us see here. Okay, so at moderate gradient, okay, dp dx is kind of moderate. So now we are in this kind of a place. So now the inflection point is somewhere in the flow, right? So but that doesn't necessarily mean that right away it will separate. So now the important thing, however, right now itself we can say that flow will separate only when the inflection point is in the is within the flow. That's one thing we know, right? But we need to know, and where in the flow will it be located? It depends on the strength of the pressure gradient, right? So something that you see in 3, I mean around 0.1 million or so, it is close to transitioning to turbulence. Okay, so now so at a moderate gradient, nothing complicated. So a critical condition is met. Now, also I would like you to notice, right? So I would like you to notice that del u del y, right? That is basically the slope. So if you look at the slope here, the del u del y, right? Now, if you look at the slope of this curve right now, okay? Now, had this separation point be higher for a very strong pressure gradient, del P del X, right? Now, the way is that I could draw this curve in several ways, right? I could draw this curve in several ways. Instead of doing it like this, let's say I could just say, I'm going to draw on top of this to sort of, give you the idea. Okay, so if I do that, or let's say if I had something like this, right? Okay, I'm going to draw another location here so that you get an idea, so that I can give you better, right? This is the circle. Now I could have several plots here. Okay, so one is of course this, right? I have one plot like this. I could have this, right? And so on and so forth, so on and so forth. Right? So these are all possibilities. These are all possibilities. And if I were to draw the, if I were to draw the, slopes, so this is something like that, this is something like this is something like this, this is something like this. These are all the lines of the slopes, okay? So, So basically 1, 2, 3, and 4, right? These curves. Now, so as you can see that these slopes are, are different, and it changes, it changes. So it changes slopes, maybe somewhere here, maybe somewhere here, maybe somewhere here, and maybe somewhere here. So where it lies is something that depends on the strength. So what you can see is that, this depending on how your, height is. So it could, this is like the angle, right? This is the slope. So now this theta, it could go here, or it could extend up to here, or here, and so on and so forth, right? So therefore, it is possible. So this is one possibility. Another possibility is also something like this. It could be something like this, right? I'm exaggerating this part actually. So therefore, what you can see is that this line is basically theta. Now it is a possibility that theta is 0, which means that I have a flow which is like this. So therefore slope, so that is the critical condition. So what we're trying to say here is that there is a critical condition. So at moderate gradient, right, a critical condition is reached, right, such that del u del y is 0. Right? We haven't seen that anywhere so far. So del u del y is 0. So in that case, what will be tau w? Because tau w is nothing but mu del u del y. So we've kind of at the wall. This is what we've been brought up with. So therefore, in here, tau wall becomes 0. So what is happening is that the wall is no more exerting any frictional force at all, or any resistance on the flow at all at this particular point. Okay, so this is when, this is the point when tau wall goes to 0. This is the point when separation will occur. So now I think you can sort of gauge from what I'm trying to say. So if del u del y, okay, is 0, right? So del u del y is 0, then tau wall is 0, isn't it? So then, you could, probably have a curve something like this. Okay, so you could actually have something like that. Right, that's the slope. You've got an inflection point, right? Got an inflection point. So in this case, okay, del u del y is 0, okay, and tau wall, here tau wall is basically 0, right? Now if this is a point, okay, this is a point which is this is essentially the, the velocity profile at which separation will occur, right? So this here separation will occur, okay? Separation will occur. Now what's going to happen next? What's going to happen next? I think by now you should be kind of understanding. So you could just sort of take this stick. So now what I'm saying is that we had, we had this slope which was here, right? Then it moved there, then it moved here in 1, then 2, 3, 4, then now it is right here like this, which is like 5. The only thing it can do now is go like this, right? So say this is 6. So if this is happening, how would you draw a curve? So basically what, we kind of little backtracking a little bit. We are kind of trying to get an idea about the flow from the velocity profile. So what we'll do here is, if that is happening, then what do we get? So then, okay, right, and you have a slope, right, you have a slope like that, right. So the only way this is going to be possible, if I were to draw something like this, then this should be my plot, right. Then I will have a plot like this, so which means that I have flow, and this is something that you guys talk about, backflow and so on and so forth. So basically the flow is in the reverse direction, as you can see, right, reverse direction. So then again, this is some kind of an inflection point, okay. So tau wall is 0. In this case, because the velocity is this way, so then my tau wall is somewhere here, okay. So this is here, so there is backflow. So we have backflow region, right. So once the flow separates, so basically we are able to get all this information, right. So the strong gradient, so basically the strong gradient causes backflow at the wall, right. And the boundary layer thickens, okay, and the main flow separates from the wall. Velocity profile is this, right. So let me sort of write there that strong gradient causes backflow at the wall, all right, at the wall, okay. The boundary layer thickens, okay, greatly, okay, and the main flow separates, okay, from the wall. Again, the velocity profile is what you see here in 5. Okay, so this is, so that's what it is, and this is the region of backflow. Okay, and used to, so therefore, and this is your velocity profile again. This is your velocity profile. Okay, I think. Now, the only thing which is important to mention here, that the boundary layer equations which we have dealt with so far, okay, cannot be used in the backflow region, which is this region, you cannot see that, okay, and this has to be the boundary layer equations are only only up to separation, so only till, say, to this figure 4 that we see, till tau wall is 0. So you can use boundary layer equations just before that, before the critical condition, which is del u del y going to 0 at the wall. Okay, so what I will do is kind of show you some pictures, from my research. In fact, you can do that very easily using some available softwares also, and that will kind of give you an idea as to how these equations are solved, and it actually gives you nice pictures, from something like Fluent maybe. Okay, so I will show you some of those results and discuss that a little bit in terms of separation, and yes, so I think we will do that. So right now I think we will stop, having talked about separation in the presence of a pressure gradient, okay, and we'll move on to different things elsewhere. So thank you very much.